Today we study ESA21H damped harmonic oscillator. The total mechanical energy E of simple harmonic oscillator is written in this form. We recall that the equation of motion is F equals mass times acceleration. In the case of the simple harmonic oscillator, the force is minus kx. The equation of motion is m acceleration plus kx equals 0. After multiplying this equation by the velocity, we can compute the power supplied to the system. So F times velocity, that is power. And we find that this is nothing but the time derivative of this conservation relation. The first term is the kinetic energy. The second term is the potential energy. The sum of the kinetic energy and the potential energy is constant motion. That means its a time derivative is always 0. Today, we studied damped harmonic oscillator. That means we have an additional force that is called a damping force. A damping force is the mass has the velocity along the right hand side, then the damping force is opposite to the velocity. So minus x dot, and its strength is parameterized by the damping coefficient B that is positive. So the equation of motion should be modified from the simple harmonic oscillator by adding additional force that is a damping force. This is the second order linear differential equation because it is a linear combination of x double dot, x, and x. Okay? So displacement, velocity, and acceleration. And the coefficients, they are all positive, definite, and the mass, damping coefficient, and the restoring force, the spring constant for the restoring force. We repeat the same job as we have done with the simple harmonic oscillator to find the relation for the conservation of total mechanical energy. What we have to do is to multiply the velocity, x dot, to the equation of motion. The first term, this one, we remember it's mass times the velocity squares time derivative. So that is the time derivative of the kinetic energy T. And this one, we remember that corresponds to the time derivative of the potential energy of the spring, as long as there is no damping force. And if B term, this damping force contribution, does not exist, then we can reproduce the relation of the total mechanical energy conservation. Okay, so we can move this one to the left-hand side, and the sum of the time derivative of kinetic energy and the potential energy, that is the total mechanical energy of the spring mass system, its time derivative is now equal to minus bx dot squared. X dot is the velocity, that is a real number, and its square is always either 0 or positive. If I multiply the damping coefficient B, that is positive definite, we find the time derivative of the total mechanical energy of the spring mass system is negative. Negative means the total mechanical energy E, that is kinetic energy plus the potential energy, decreases as time goes by. Okay, next we solve the equation, this equation of motion for the damped harmonic oscillator. In the previous class, we made use of the completing the square to reduce the arbitrary second-order linear differential equation with real coefficients into this form. The factoring out this exponential factor made this first-order derivative in the relation for the equation of motion for this y function. Therefore, we find this a very trivial second-order differential equation. We first consider underdamped motion. Underdamped motion is the case when the spring constant satisfies the relationship between among the spring constant, damping coefficients is given like that. This means that this one inside the square root is positive. So this means the spring constant is strong enough to win the game with the damping coefficients. So a little bit weaker damping force is applied to the system, then we say it is an underdamped motion. All right, so we remember the solution of this equation, because this is a positive number, is the same as a simple harmonic oscillator, except that this one is replaced with this k over m subtracted by b over 2m squared. All right, so it is not a characteristic angular frequency of the corresponding simple harmonic oscillator, a little bit modified one. Because of this subtraction, this frequency of the oscillation, omega, is slightly smaller than the typical angular frequency for the corresponding simple harmonic oscillator. Anyway, the mathematical structure of the solution is the same. It is a linear combination of e to the I omega t and e to the minus I omega t. We know they are a linear combination of cosine and sine according to Euler's formula. Therefore, it is a sinusoidal function. We remember the sum of two sinusoidal function is another sinusoidal function. The amplitude and phase may vary in comparison with each contribution. Therefore, we have oscillating factor. However, we have an exponential factor that decreases arbitrarily small as time goes by. Therefore, multiplication of this exponential factor that decays as time goes by and the oscillating factor result in this kind of shape of the solution of the underdamped motion. Underdamped motion has an oscillating structure but the amplitude, it is not a periodic function anymore. This is a periodic factor, but because of this exponential factor, damped harmonic oscillator is not periodic anymore. The shape decreases. The range of oscillation decreases as time goes by. This is the typical structure of the underdamped motion of a damped harmonic oscillator. Next, we consider the case when the damping coefficient is quite large. In that case, inside the square root, we have b over 2m squared subtracted by k over m is a positive. In that case, the sign is flipped. This one, again, a trivial second order linear differential equation, but because this is a negative sign, our final result for the y function is a linear combination of two exponential functions. It is either increasing or decreasing. We have additional overall factor that is identical to this. We compare this exponential factor and this. We know k and m are positive, so this value is slightly smaller than b over 2m. Therefore, as t goes to infinity, this product of exponential functions and this product of these exponential functions, both of them decays as time goes by. Another way to represent this solution can be done by introducing cosine hyperbolic and sine hyperbolic with the same argument. As I stated, because b over 2m is greater than the square root of this, the solution decays to 0 as t goes to infinity. As the last step, we consider critically damped motion. In that case, critically damped motion is achieved when this term vanishes. That means b over 2m is identical to the angular frequency of the corresponding simple harmonic oscillator. So equation of motion for this y function is trivial. That is a linear combination of constant and linear time-dependent term. As a result, we have this kind of form. The exponential function decreases very rapidly, and a linear function either increases or decreases linearly. As a result, the typical shape of the resultant motion is something like that. So there is no oscillation in the critically damped motion. So critically damped motion, at most, there is a bumper. Over damped motion, it is strictly decreasing to 0, and we have usual oscillation in the underdamped motion. Okay, that's it for today. Thank you.